thrilled and glad to welcome Professor Roberto Gomez-Garcia with us in this webinar. And just a short introduction about Professor Roberto Gomez-Garcia. Professor Gomez-Garcia received the degree in telecommunication engineering and the PhD degree in electrical and electronic engineering from the Polytechnic University of Madrid. Since 2006, he has been an associated professor with the Department of Signal Theory and Communications, University of Alcala in Madrid, and he has been for several research stays with the C2S2 department, XIM Research Institute, University of Le Mans in France, Telecommunications Institute of University of Aveiro in Portugal, with US Naval Research Laboratory, with Microwave Technology Branch in Washington, DC, USA, and in Purdue University in West Lafayette, USA. His current research interests include the design of fixed and tunable high-frequency filters and multiplexer and planar hybrid and monolithic microwave integrated circuit technologies, multifunction circuits and systems, and software-defined radio and radar architectures for telecommunications, remote sensing, biomedical applications, and in which he has authored and co-authored around 100 journal papers. And Professor Gomez-Garcia was the recipient of the 2016 IEEE MTTS Outstanding Young Engineer Award and is IEEE Circuit and System Society Distinguished Lecturer for the years 2020 to 2021. Okay, so Professor Gomez-Garcia, the stages are yours, and please.
Okay, so thank you very much for this very kind introduction. For me, it's really a pleasure to be here today giving this talk within the IEEE Circuit and Systems Society Distinguished Lecture Program. So I would like to thank Technion for his very kind invitation to be here, and also to the Israel CARS chapter. It's really a pleasure. So today I will present my talk, Reconfiguring the World, Adaptive Transfer Function and Multiband Filtering Devices for Emerging Wireless Systems. So basically, the purpose of this talk is trying to see which are the current trends on the field of highly advanced microwave passive filtering components. And we will see that as current trends, we need to go to even each time more performance or higher performance devices that can include or may include reconfiguration in the transfer function and also multifunctional capabilities. So basically, the outline that I will follow in this presentation, I will start with a brief introduction in which I will try to motivate the topic of this talk. So why this kind of multifunctional and highly reconfigurable, highly adapted filtering components will be needed in future radio frequency front-end chains. After that, once we have seen this motivation, I will split this talk into different parts. In the first part, we will focus on the first topic about multifunctional radio frequency filtering components. And in the second part, we will see different examples or very challenging, highly reconfigurable filtering components for these new radio frequency systems. And then I will conclude with a brief summary of the most important remarks of this presentation. Well, we all know that the radioelectromagnetic spectrum resource is very scarce, so it's exploited by a large number of applications. And if we think in our wireless communication terminal, we want each time to have more functionalities. So basically, we want a very widely connected society in which our device can be connected to any other device, any other network, at any time, and seamless. So basically, this means that if we want to provide all these multi-service capabilities for our mobile communications terminal, this means that we need to increase a lot the hardware complexity of our terminal. So in order to have an idea, we can see here in the right-hand side of the slide what would be today obsolete multifunctional transceiver that is capable to support different standards in the same module, in particular 2G, 3G, and LTE. So basically, we can see that in order to make our terminal to be able to support all the signals associated to the different service for which we want our terminal to operate, we need to increase a lot hardware duplexity. So for example, in order to properly acquire all the signals corresponding to the different services that we want our terminal to support, we need to increase a lot the number of filters. So here we can see that we will need 20 filters. That is a lot. And if we think even in more advanced modules in which we want even more services to be supported, we will need to increase even more the number of filters. So basically, this is not a very good approach if we think in terms of complexity and size. Of course, a more efficient approach will be to replace all these static filters that we have here by a single filtering unit with tunable capabilities. That means a single filter that is capable to adjust its transfer function to the spectral characteristic of the signal that we want to acquire at each time. So of course, going from this 20 filter static solution to a single filter tunable solution will allow us to reduce complexity and size. But also we need to think that in addition to filters, we have some other components. For example, here we can see amplifiers, mixers, and so on. So in general, we also have a large number of active circuits. So we can see that also in previous approaches of multifunctional transceiver, we need to increase the duplexity in terms of the active circuits that we incorporate. That basically means that we will increase the DC power consumption and the cost of the full terminal. So of course, another efficient approach will be trying to co-integrate, for example, the amplification function along with the filtering function in what will be a multifunctional filtering amplifier device. So I want to remark that another trend, in addition to replace all these static circuits by a single tunable filter, is trying to co-integrate functionalities in order to have circuits that can provide several functionalities in the same device. So this is why I remark here that the future will be going tunable and multifunctional in order to reduce complexity, size, power consumption, and cost of these radio frequency transceiver chains. But as we have seen before, since the electromagnetic spectrum is a very scarce resource, we will have always interference problems. That means that our terminal can be damaged by signals from other systems that are also operating or making use of the electromagnetic spectrums. So even if most of the interference that we may have can come from other systems, what we call out of systems interference, we also can have some interference that comes from our systems. If we think, for example, in the leakage that we can have from the transmitter to the receiver part in a transceiver architecture. So this means that in order to cope with this problem of interference, we also need high performance interference protection mechanisms that can be accomplished at the signal processing level, but here we will see some solutions at the hardware level that can be more efficient because we will directly mitigate the interference signal in the radio frequency front end part. So here we can see what will be a very basic scenario in which we have a very basic block diagram of a wideband receiver. Basically, we have the antenna, the radio frequency filter. After that, we have a low noise amplifier, and then we will have the rest of the receiver. And we can see here that our system is exposed to the desired signal that we want to acquire, but also to some interference that comes from other systems. So basically, we can have two different scenarios. If we take a look to the scenario one that is represented in the right low hand of the slide, we can see that in this situation, all the interference that are represented by means of green arrows are far away in a spectrum from the signal that we want to acquire. So in that case, the situation or the problem of mitigating this interference will not be very critical because the only thing that we need is a radio frequency filter with enough selectivity that we can accomplish by increasing the order of the filter, putting more resonators, or by generating transmission zeros in the out-of-band region that will require more complex circuit architectures involving cross-coupling between resonators. But then in this scenario 2, we have a more critical situation, because here we can see that in addition to the out-of-band interference that are far away in frequency from the signal that we want to acquire, another interference appears in the close proximities to the desired signal within the bandwidth of our systems. So in this case, we will need the transfer function of our filter to be more complex. That means that in addition to have the capability to provide the bandpass filtering for the bandwidth of the receiver, we will also desire in this filter the capability to create some stop band of notch frequencies to suppress this in-band interference that can appear close to the desired signal. And the situation is still more critical, because at the very beginning, we don't know in which frequencies these interference signals can be allocated. So we will want these notches that we can create inside the filter to be adapted, also in frequency and in bandwidth, because the interference signal can have different bandwidth characteristics. So at the end, what I want to reflect here is that the complexity of the transfer function that we need to incorporate in our filter is higher if we want to properly cope with highly congested radio frequency interference scenarios. So once we have introduced the motivation of why it's so important to have highly reconfigurable filtering components to replace a large number of static filters, but also the necessity of multifunctional circuits in order to combine together different functionalities on the same device, we will see in the first part of this presentation some examples of multifunctional radio frequency filtering components. The second part will be devoted to highly adapted filtering devices. So the purpose of this first part is to understand why the multifunctional design philosophy for radio frequency filters or radio frequency circuits in a broader sense is so convenient. So basically, we think in filtering devices. That is the main purpose of this talk. So we will focus on multifunctional devices that provide as one of the capabilities the filtering operation. The purpose is to combine the filtering operation with other types of radio frequency analog processing functionalities. For example, we can see here power division, amplification, impedance transformation, even antennas, to design filtering antennas, phase shifters, and so on. So these will be examples of circuits that can provide several functionalities in the same volume. And why it can be so beneficial to pass from the monofunctional approach to the multifunctional approach? So here we can see some advantages. First of all, if a single device can provide several functionalities, it seems quite obvious that we will have a more compact solution, because a single circuit can provide at the same time different functionalities like amplification, filtering, power division, and so on. Also, in general, we can take benefit of the co-design of the different functionalities of the same circuit in the same circuit. That means that we can optimize the performance of each functionality by means of this co-design. And another advantage that is quite obvious if we think in this multifunctional approach when compared to a conventional in-series cascade connection of different monofunctional blocks is that we will no longer need transmission lines or radio frequency interfaces between the monofunctional blocks. And these additional radio frequency interfaces in general introduce more insertion loss levels and also increase size. So another advantage is that we will decrease insertion loss. That is an important parameter, especially in the receiver side. So here we can see what will be at the block diagram level in order to understand better this comparison between the classic monofunctional approach and the multifunctional approach. an example of a filtering power divider that could be designed by means of the multifunctional approach and by means of the multifunctional approach. So we can see here that in the monofunctional approach, what we will make in order to have a radio frequency subsystem that can provide the power division and the filtering capability is to add at the outputs of the the power device 2 filtering units. So basically, the whole structure will provide this power division filtering capability, but we need to add 2 filters with the corresponding radio frequency interfaces of matching sections between the outputs of the power divider and the filter. So we can think that this solution will not be very efficient in terms of circuit size. So the multifunctional approach, and we will see later how we can do that, will consist of directly co-integrating the filtering capability inside the power divider. So even at the block diagram level, it seems quite obvious that this monofunctional approach seems to be more convenient in terms of circuit size. Okay, so we all know that, especially in the radio frequency band or in the microwave range, the most convenient or the most conventional approach to design a microwave filter is to use electromagnetic coupled resonator networks. But in this case, in order to design these multifunctional filtering components, we will see another approach to create the filtering capability in this kind of multifunctional radio frequency devices that we will see in order to connect a little bit with the digital world. So basically, the approach that we will see to realize the filtering capability also in the radio frequency band is the so-called signal interference approach that basically is inspired by classic digital transversal filtering techniques. So I guess that most of you are quite familiar with classic techniques to design digital filters or discrete time domain filters. So basically, one approach is to use transversal architectures in which the input signal, as we can see here in this flow diagram, is divided among different signal propagation paths into different components. So in these paths, we have very basic operations such as a delay or an amplitude scaling factor. And how we get the filtering action is by means of the combination in the output terminal of all the signal components in which the input terminal has been split once they have traveled through the different propagation paths of this configuration. So this is how we design a digital transversal filter. So the idea is trying to extrapolate this kind of principle to the radio frequency domain. And how we can do that? There are several ways to do that, but since most of the examples of the prototypes that we will see will be developed in planar radio frequency technologies, we will make use of a solution that made use of transmission lines, because the transmission lines is one of the most classic example of circuit elements in the radio frequency domain. So here we can see what will be a transversal filtering cell in the radio frequency domain that is inspired in these digital transversal filtering concepts. So basically we can see here that our transversal filtering cell in the radio frequency domain is composed by 2 different transmission lines that are connected in parallel. So basically, as design parameters, we have the characteristic impedance of the 2 transmission lines and also the electrical length. And from this representation, it is quite obvious that this is a bypass signal propagation configuration, because the input signal is split between the 2 transmission lines that we have in parallel in 2 different components, and then we get the output signal from the combination of the 2 signal components once they have traveled by means of the 2 propagation paths. So for example, if we want to create a dual band response, a dual band bandpass response by means of this solution, what we will need is to select these parameters in order to create a constructed interference between the two signal components within the passband ranges of the dual band transfer function. And outside the transmission bands, what we will be is to have a destructive interference between the two signal components, signal cancellation, in order to create transmission zeros and this, by this way, to increase the rejection levels that we have in the output band region. So this is how we can get a dual band response, for example, but we can get some other kinds of filtering responses. So here we can see two examples of what will be very high performance microwave planar filters based on this transversal signal interference approach. So the first example corresponds to a dual band filter, and the second example to a low pass filter. So in the first example, we can easily recognize what will be our transversal filtering section. Here we have the two transmission lines paths. So here we have one path and the other path, and we connect in cascade several sections, several replicas of this section in order to increase the selectivity levels of the overall transfer function of the circuit. So here we can see what will be the representation or the comparison between the measurements and simulation results. And we can see that we obtain a very high selectivity dual band filtering response, in which we have the two dual passbands, and we have very sharp transitions between the transmission bands and the output band rejection areas. I can tell you that if you try to design this kind of transfer function with a classic coupled resonator solution, you will need a very complex circuit arrangement involving cross-coupling between resonators and so on. But here, with this very simple configuration, we are capable to obtain a very high performance transfer function. But we can also apply this kind of principles to design some other kind of filters. For example, here we can see what will be the application of this kind of transversal signal interference principles to design a low pass filter with very high performance. So we can see that the transition that we have between the transmission band and the stop band is extremely sharp, very sharp transition. But in addition to that, we have an stop band bandwidth that is very broad, much broader than what we usually get with more conventional low pass microwave filter configuration. So we can see that the stop band goes from 1 gigahertz to more than 5 gigahertz. That is very wide, if we take into account that in general, transmission lines are frequency periodic elements. Okay, so once we have introduced the kind of elements that we will use to design our multifunctional components, how we can do that? So here we will see some examples of multifunctional components. The first one is based on a filtering power divider using a Wilkinson-type arrangement. So basically here we can see what will be the conventional configuration of a Wilkinson-type power divider, in which the input signal is split between two branches. We have an isolation resistor in order to provide isolation between the two outputs and to assure that we can have input power matching level in the three terminals of the device. So basically the idea is to replace the classic transmission lines that we have in the conventional power divider by this transversal signal interference filtering cell. So basically if we do that, we will pass from a circuit that just provide the power division capability to a dual functionality circuit that can provide both the power division capability intrinsic to the power divider scheme, but also the filtering capability that is created by the transversal filtering sections that are replacing the transmission line segments. So in the bottom part of the slide, we can see what will be the representation or the photograph of a proof of concept validation of this kind of approach for a 4-band example. So basically we can see here what will be the transfer function from the input to one of the outputs. We can see in the black line, continuous line, that will be the measurement that we get a power division functionality for the 4 bands. And then we have a filtering capability that is produced by the transversal filtering sections. Of course, we have insertion loss that increase when we consider higher operational frequencies, because we know that as we increase the frequency, losses from the conductor and the dielectric are higher. Here we can see what will be the input and output matching performance of this device, and we can see that in the 4 bands we have a very nice power matching performance. So this circuit will provide all these functionalities: power division, filtering capability with the stop bands isolated by means of transmission zeros, and also multiband operation in 4 bands. But we can apply this kind of device to build even higher level radio frequency subsystems. For example, we all know that one classic type of amplifier is the multi-branch amplifier, because allow us to increase or to improve the non-linearity performance we compare to a single branch amplifier. So in this kind of devices, in this kind of multi-branch amplifier, we always need power divisions and power combination blocks. So basically what we propose here is to replace the classic power division and power combination block by means of a single band version of this kind of power divider with filtering capability that we have introduced. So if at the same time we have in each branch of the multi-branch amplifier some low order filtering, we can get an overall response that provides power amplification within the operational band of the overall circuits, but at the same time, a very high selectivity filtering action obtained from the congregation of the response of the low order filters and the filtering action of these filtering power dividers, and combining that we put up the input and up the output. So in the bottom part of the slides, we can see what will be the validation of this concept. So we can see here the low order filters that we put in each branch. Here we can see the amplification sections in order to provide power gain. And in the input and at the output, we have this single band filtering power divider multifunctional circuits. So here we can see in black line what will be the measurements of the overall transfer function. We can see that within the operational band, we have a power amplification that is higher than 10 dBs, but at the same time, the overall transfer function is the one of a very high selectivity field. So this is a circuit that at the same time provides the power amplification and the filtering capability. In green, we can see what will be the comparison or the transfer function of the low order filter. So it's quite obvious to see that the selectivity of the overall circuit is much higher than the one provided by the low order filter. Also, we can apply this kind of multifunctional approach to other components. For example, in basic microwave engineering courses that we take in the basic studies, we know that a way to design an impedance transformer, that is a circuit that allows me in a certain operational bandwidth to pass from a real impedance to another desired real impedance. So a conventional solution to do that is to put in cascade several transmission lines. So basically what we propose to introduce filtering capability to this kind of impedance transformer is to replace again these quarter wavelength transmission lines by means of the transversal filtering sections that we have introduced. Of course, these transversal filtering sections needs to be designed with regard to the impedance level or to an impedance level equal to the characteristic impedance of the transmission line segments they are replacing. So if we do that, we can pass from a classic impedance transformer to a new filtering impedance transformer. That means a circuit that at the same time provides the impedance transformation and the filtering capability. So in the bottom part of the slide, we can see what will be the validation of this concept for a dual band design. So we can see here for a 3-stage circuit that we have replaced the first transmission line and the third transmission line by means of our transversal signal interference filtering cell. And basically by doing that, we can convert a loading impedance that in this case is of 25 ohms into a desired 50 ohm impedance within the two operational bands defined by the transversal filtering section. So basically, if we represent here the power reflection coefficient, we can see that inside the bands, we have very low reflection. That means that we have very nice matching with regard to the impedance that we want to see here. But then if we represent the transfer function that we will have from the input to the loading impedance, we have the one corresponding to a dual band filter. So this is another example of a dual functional microwave circuit. And as the last example to conclude with this first section about multifunctional components, we see here the application of this transversal filtering section to realize a balanced or differential mode bandpass filter. A balanced or differential mode bandpass filter can also be understood as a dual functional component, because in this case, the functionality that is provided by the circuits depends on the type of excitations that we are putting into the two-port input terminal of our circuit. So basically, differential mode filters are designed by means of symmetrical configuration. That means circuit configurations in which we can identify a symmetry plane, and we will incorporate the transversal filtering section that we have presented in the past in each of these symmetry parts in order to increase the filtering capabilities. But the operational principle of this kind of device is easy to understand. If one thinks in classic differential mode amplifiers that we learned in the first courses of electronics. So if we applied a differential excitation at the two nodes of the two-port input terminal, that means equal voltage but with opposite phase, basically what we will see here in the symmetry plane is a short circuit. So we can design this half part of our circuit when we have here the virtual grounds coming from the differential mode excitations to behave as a bandpass filter. So basically, if we have this differential mode excitation within the passband of the transfer function of this side, we will allow transmission. But what happens if we applied a common mode excitation? That means equal magnitude and equal phase in the 2 points of the differential mode of the two-port input. So in this case, in the symmetry plane, what we get is a virtual open circuit. So when we have here virtual open circuits instead of virtual ground connections, we can convert what was the bandpass transfer function into a bandstop transfer function. That means that within the differential mode bandpass, now we will not allow signal transmission. So basically, in this device, with the differential mode passband, we allow the transmission of the differential mode, but we don't allow the transmission of the common mode. So here in the bottom part of the slide, we can see what will be a validation of this concept. And we can see here what will be the simulation and measurement results when one applies a differential mode and a common mode excitation. We can see that for the differential mode excitation, we have a transfer function that is the one of a bandpass filter with a very high selective performance, because we have very sharp transitions from the passband to the output band with transmission zeros. But then if we apply the common mode excitation, the transfer function that we get is this one. So we can see that within what was the differential mode passband, now we don't allow the transmission of the common mode. So this is another example of a multifunctional circuit. So then to start with the second part of this presentation, we have seen before why it's so important to design filtering components that can provide very high levels of reconfiguration in the transfer function, because we will be capable of replacing classic solutions in the transceiver in which we have a large number of static filters by a single filter that can acquire all the signals, regardless of the center frequency and the bandwidth of the signal. Okay. So what we understand by reconfiguration. So basically, reconfiguration is the capability to modify or to adjust the performances of the transfer function in the same circuit. And if we take a look to the literature on this subject, we can see that this subject has been well established for a basic approach of bandpass filter or bandstop filters that allows to control the center frequency and the bandwidth. But what about more challenging designs? Because if we think in the applications, the wireless applications that will come in the future, we need to design more challenging reconfigurable filters. For example, fully adapted filters in which we can commute in the same circuit between a bandpass and a bandstop mode, and at the same time to have control of the performance of each mode. Also fully reconfigurable multi-band filters, multi-pass band filters to acquire various signals at the same time, or multi-stop band filters to reject several interference signals simultaneously. Also, it's very desired to co-integrate these dynamic multi-interference suppressors filters with broadband filters if we think in spectrum exploration, radio frequency front ends, and also reflectionless tunable filtering components in order to avoid the creation of reflections. Okay, so then we will see several examples of these high challenging reconfigurable filtering devices. And we will start by introduce a device in which we are capable to select inside the same device a bandpass mode for signal acquisition or a bandstop mode to reject an interference, and at the same time having control in center frequency, bandwidth, and rejection levels for the two functionalities. And this is not a very easy approach, because if we go to the test books, to the basic literature book, and we see how we can design, for example, a second order bandpass filter and a second order bandstop filter, we will see that in both cases, of course, we need two resonators because it's a second order solution. But if we take a look to the configuration that we have for the bandpass case and for the bandstop case, we can see that these configurations are very different. We can see that the impedance inverters or the impedance inverters that we have in the configuration are placed in very different positions. So basically, seems to be quite different to co-integrate at the same time two configurations that from the topological point of view are not similar. So what we propose is to think in a very different approach that doesn't try to merge these two configurations that are very different. So basically the approach that we propose to design this high performance bandpass, bandstop, reconfigurable transfer filter is the following one. What we use is what we call a bandpass bandstop section that can generate transmission jitters. So basically, for those that are not conventional with this kind of representation for coupled resonator filters, the black nodes will be resonators, and these gray nodes basically are just connecting points. So what we will have from the input to the output is a direct transmission path. But we put in cascade several sections of what we call bandpass bandstop section. And each section is composed by two resonators that are coupled to the main transmission path by means of impedance inverters. So basically, we know that at the resonant frequency, a parallel resonator provides an input impedance that is an open circuit. But here we have an impedance inverter. That means that at the resonant frequency of the resonator, we will create a transmission zero by each of these two guys that we have here. So basically, if the resonant frequencies of these two guys are put at different positions, we are capable to create a transfer function like that, like the red one that we have, in which we have the two transmission zeros coming from each of the two resonators, and in between we have a transmission band. So the strategy is to put in cascade several of these sections in order to have a transfer function, overall transfer function, that is the cascade of the individual transfer function defined by each of these sections. So at the end, we are capable to design a transfer function like the black one, in which a transmission zero is generated by each resonator. So we know that there are well-known techniques to control the resonant frequencies of the resonator. So this means that we can control the performances of the transfer functions by just control the resonant frequencies of the resonators. So for example, if we allocate the two transmission zeros generated by this cell at the center frequency of the other two resonator cells, we can pass from a bandpass mode to a bandstop mode. So this is a very smart idea to design a filter in which just by controlling resonators, resonant frequencies of resonators, we can either have a bandpass or a bandstop transfer function. And we can see that we can control the performances of the transfer functions in both modes by reconfiguring these transmission zeros. So here we can see what will be a validation of this concept, in this case in substrate integrate waveguide cavity resonator technology. So each resonator basically is designed, I will not enter in the microwave details, but it's designed as evanescent mode cavity resonators, and we couple these resonators to the main line by means of transmission lines impedance inverters. So here we connect in cascade two cells in order to hide a two-stage design, and we can see what will be here the measured performance for this kind of device. So we can see here what will be several bandpass transfer functions in which we can reconfigure the center frequency, the bandwidth, and we do all this by just controlling the transmission zeros that are generated by the different resonators. Here we can see how we can control even only one side of the transmission band that we generate, but then when we put this transmission zero in the same position as this transmission zero at the center frequency of what was the passband, we pass to a bandstop mode. So this is a practical validation of the previous concept. The second kind of circuits that we will present is the design of a reconfigurable multi-band bandpass filter. That means a filter in which we have several transmission bands that can be reconfigured in center frequency and bandwidth. And if we think in the classic approach to design this kind of filter, well, the most classic approach will be to put in parallel several independently tunable filtering units, each of one directed at acquiring each of the signals. But basically, this approach is not very efficient if we want to have a solution that can be generalized to any number of bands or signals that we want to select with low circuit size, because we can understand that the higher the number of signals that we want to acquire, then the higher the number of branches that we need to put. And also to design in microwave branch these signal divisions and signal combination blocks when we increase the number of branches is something that is not very easy to do. So basically, this classic solution is not very efficient in terms of size, in terms of sensitivity of the tuning of one of the bands that will affect the other bands and so on. And this other approach also has very related problems. So basically what we propose is to design an approach in which each of the stages can provide by itself all the bands that we want for our circuit. And of course, as in the previous case, we can put in cascade several replicas of these cells to increase the selectivity. So basically, this is what was called a multi-resonant quasi-bandpass cell that can provide all the bands by itself, and by making tunable the resonator that we put in the cell, we can achieve reconfiguration performance for all the bands. So here we can see the validation of this concept. If you want more detail, you can go to this here. I try to put the main reference if you want further details about the design process, the operational principles of this kind of solution. But here we can see what will be the validation of this concept for a two-band third-order solution. So basically, we put here one cell, another cell, and a third cell. Here we can see the interaction between the different cells, and in the top part we can see what will be the measurement results for different reconfiguration states. How we achieve reconfiguration is by adding, in this case, mechanically reconfigurable trimmer capacitors to change the resonance of the resonators. So basically, in the first graph, we can see different transfer functions in which we are changing the positions or the locations of the two bands and also the bandwidth of the two bands. Here we can see how we can keep static one of the bands and reconfigure the other band. And here we can see how we can even merge or combine the two bands to configure a wider transmission band. So basically, this is a very flexible solution of dual band reconfigurable filter. Also, we can extrapolate this solution to design an stop band version of the previous one that will be capable to provide us a multi-band stop band filter. That means a filter that will provide the capability to suppress different interference in the same circuit. And again, the solution that we will present is more efficient than the conventional solution of putting in cascade several independently tunable bandstop units that will be the classic approach to design a multi-notch filter, because in this case, we will need to increase the number of cells that we put in cascades in order to have more stop bands, and also this will lead to an increase in the insertion loss level that we have in the passband region. So basically what we propose here is extrapolation of the previous concept to the multi-stop band case. So basically, again, what we put is a multi-resonance cell that can provide by itself all the stop band that we want to create, and also by tuning the resonance frequencies and the couplings that we have between the resonators of the multi-resonance cell and the direct input to output transmission path, we are capable to adjust not only the center frequency, but also the bandwidths of the stop bands that we will create in order to have a flexible signal mitigation in terms of bandwidth and center frequency. So here we can see what will be the validation of this concept, in this case, to create 3 stop bands with second order characteristics. And here we have the measurements capability. So basically, we can see what will be the 3-band transfer function that we get and how we can tune one of the stop bands when we keep static the other stop bands. Here we can see how we can tune in bandwidth one of the stop bands when we keep static the lower and third stop band. For example, if we want to pass from the suppression of a narrow band interference to a wider band interference. And in the bottom, we can see how we can even merge the different stop bands to create a single and wider stop band that can be also reconfigured in terms of center frequency and bandwidth. So as a final example, we can even co-integrate this kind of tunable multi-stop band circuits with wideband bandpass filters in order to design a filter that at the same time can provide a very broad band acquisition with multi-notch or tunable multi-notch capability to suppress some interference that can appear in this wide bandwidth acquisition part that we did now for our circuit. So here we can use several approaches, but remember what we have learned about signal interference circuits. A good way to create or to design a wideband filter that at the same time incorporate these tunable in-band notch bands to suppress interference is to add a third path to the transversal filtering section that we have introduced before. So basically, with the first and second path, we are capable to create the wide bandpass transfer function that we have seen before, but through the joint action of the first part and this third path, in which we will incorporate some tunable resonators, we are capable to create these notched bands. So basically, the overall transfer function will be the one that comes from the combination of these two partial transfer functions. So basically at the end, what we get by means of this modified three-path transversal filtering section is the response of a wideband filter with a notch inside the band. And of course, by tuning the resonator that we have here by means of trimmer capacitors, we are capable to reconfigure the position of this notch that we are creating inside the bandwidth. So basically, we put in cascade several of these three-path transversal filtering sections. We are capable to design a higher selectivity wideband filter, but at the same time, we are capable to increase the number of controllable notch that we have inside our passband. So this will allow us to deal with very different scenarios because we can allocate this tunable notch either to shape a wider stop band inside the passband, or even, for example, to create a wide stop band and a narrow band notch inside the overall passband defined by the first two paths of the transversal filtering section. So here we can see a validation of this concept for a two-section case, for the two-section case. So basically, we have what will be the blue response. So if we don't consider the notch that we have here, this blue response without the notch will be the one that is created by this lower side of the circuit, but we have added a third transmission path in each of these transversal filtering sets. So basically, each of these paths will create a notch inside the operational range of the filter. So basically, as we have two sections, we will be capable to create two notches. And by tuning these resonators, we are capable to make the notch that we are creating here reconfigurable to suppress interference that can appear within the wide operational bandwidth created by or intended for our receiver. So here we can see how we can, for example, reconfigure the upper part, the lower part, notch, while keeping static the upper one. And here we can do the opposite, how we can reconfigure in center frequency the upper part notch while we keep static the lower band notch. So basically in this talk, what we have seen that in order to be capable of implementing very highly versatile radio frequency front-end chains with lower size, high flexibility, and at the same time low DC power consumption, we need to incorporate to these new radio frequency chains reconfigurable and multifunctional components, not only for the acquisition of the signals that we want, but also to suppress the interference that may appear in our systems due to the current situation that we have of a very crowded electromagnetic spectrum. In the case of multifunctional radio frequency components, we have seen several examples of these devices, all of them using the so-called transversal signal interference philosophy that allows the creation of very high selectivity filtering functionalities for single band and multi-band applications. And we have seen apply this approach to design filtering power dividers, filtering and impedance transformation circuits, and even balance of differential mode circuits. And in the second part, we have seen several cutting-edge examples of very highly adaptive radio frequency filtering components. For example, filters that provide either a bandpass or a bandstop functionality that can be reconfigured in center frequency bandwidth and rejection levels. Also, we have seen examples of multi-band bandpass filters and multi-band bandstop filters for the simultaneous acquisition or the simultaneous suppressions of different signals. And also we have seen how we can co-integrate these multi-notch interference suppression cells with broadband filters that can be designed, for example, in a spectrum exploration radio frequency chains. So here I would like to acknowledge several professors that has cooperated with me to obtain the result that I have shown in this presentation, mainly from United States during the research state that I was doing during the last few years. Also would like to thank to some PhD students and local operators that also has been essential individuals in the works of this presentation. And of course to the University of Alcala, to the community of Madrid, and to the Spanish Ministry of Science for the logistics support and the research funding that they have provided during this year. And thank you very much for this invitation. I would like to thank again to Technion for this very kind invitation, and also to the Circuit and System Society for giving me the opportunity to these 2 years to make these presentations under the framework of the distinguished lecture program. So thank you very much. And if you have any questions, I will be very happy to reply. Thank you.
Thank you, Roberto. Thank you very much. Any questions from the audience, please? As usually, you can either raise your hand or write the questions in the chat. Okay, I see that there are no questions.
Okay, I don't know if it's good or bad. I don't know if it's because I was very clear or maybe...
No. We have questions. I'll tell you something. We have the problems with the internet connection, so that's why we have some delays. Okay, so we have the questions.
In any case, if someone comes with a questions later or during these days, please feel free to contact me at this email address, because I will be very happy to discuss any aspect or any topic of this presentation. So I am available.
But let's read the questions in the chat.
Okay.
So there, yeah. The question is, can you please refer to the size of these solutions? This is a question from Benjamin.
Yeah, of course, most of the circuits that I have presented are for planar technologies. That means that maybe they can be convenient solutions for, let's say, receivers of radar systems, but for example, not for mobile communications. Here, I have presented some examples on microchip technology, but using these approaches, if you go to, for example, if you find my works in IEEE Explore, I have also some examples of circuits that make use of this kind of solutions for integrated circuit solutions that will be more appropriate for mobile communication systems. Also, if you want to design these kind of devices for, let's say, satellite communications, in satellite communications, what is important is to have high power handling capability. So in this case, you will need to go even to a higher size volume solution like waveguide, because in that case, what is important is to have high power handling capability. So replying to your question, the size in this case, I will say that is medium. Okay, it's not as small as in integrated circuits, of course, and not as high as in waveguide technologies. But at the end, what defines the technology that you need to use is the requirement that you have in your applications. In satellite communications, you need waveguides because you need to handle very high power signal levels. In mobile communications, especially in the receiver, what is better is to have an integrated solution. But maybe in radar modules, you have something in between. So let's say that these circuits will be directed mainly for this kind of applications, applications in which you don't need very miniaturized size, but also you don't need very high power level handling capability performance.
There is another question, which is how small can the device be? The question is from Gardeshore.
Okay, yeah. How small the device can be. So at the end, as I have told, if one uses this technology, to miniaturize size, you have several options. The first one, of course, is using a substrate with a higher as possible dielectric permittivity. But when you increase the dielectric permittivity of the substrate, that you decrease the size of the circuit, then you increase the insertion loss. So basically the trade-off there is that when you miniaturize your circuit by using a very high dielectric permittivity constant, then you have as a trade-off an increase on insertion loss. And then another solution that you can get is to use maybe meander line arrangements. But at the end, the degree of miniaturization that you can use by means of this solution is not very big. If you go to higher frequencies, for example, to the millimeter wave range, now there are some words. Even I have been cooperating with some research groups in Australia about the integration of this solution for millimeter wave design. In that case, you can obtain very highly miniaturized designs, but this is because you are going to very high frequencies. So the waveline of the device, the waveline, becomes very small. But at the end, how small can be? So depends on the frequency range, the dielectric permittivity of the substrate, and also the miniaturization techniques that you apply.
Okay, thank you. There is a comment from Moti Korev. You assume 50 OHM termination, which is not the real case.
Okay, it depends. Well, in fact, this was one of the motivations of the multifunctional approach, that in the multifunctional approach, in which, for example, here, you connect, in the monofunctional approach, when you connect different blocks to obtain the multifunctional or the multifunctionality, you need all the blocks to be matched to 50 ohms. So in the microwave region, in waveguides and planar technologies, this is very usual. In general, if you buy devices in these technologies, in general, you find that these devices are always terminated or designed for 50 ohms. But in the multifunctional approach, you don't need inside the circuit to have all the functionalities matched to 50 ohms. And this is why you can optimize the performances of the different functionalities. But it's true that in all the examples that I have presented at the end, I want the terminals of all my device to be matched to 50 ohms. So in microwave domain, in planar technologies, waveguide technologies, and so on, this is a very usual situation. The requirement is to have 50 ohms matching, but I know that in some other technologies and applications, this is not true.
Thank you. Thank you very much. It's so clear that there are no questions, but still there are questions.
Okay.
Most of the examples shown were based on transmission lines. Did you also try to implement using discrete lumped parts?
Yes, this is a good question. Indeed, at the end, you can extrapolate all these principles to other technologies. For example, you know that we have a lumped element equivalent of a transmission line. So even these specific devices that I have presented that relies on transmission line can be transferred to lumped element implementations if one thinks in the equivalent lumped element circuit of a transmission line. But beyond that, we can also apply this kind of philosophies to filtering devices that are shaped by resonators, in which we use LC resonators. So the reply is yes, this kind of philosophy will be general not only for transmission lines, but also for lumped element circuits. And if you go to my previous works that maybe you can find in IEEE Explore, if not, you can write me an email and I will be happy to provide you some references. I have done some examples of these multifunctional devices and tunable devices in other technologies, not only lumped element, but also acoustic wave technologies that are very desired, for example, to mobile communications, because there you need very high quality factor filters.
Thank you. do you see the question regarding the reconfigurable filters? Yeah. Did you look into phase response dispersion vs the classical approach, signal distortion?
Yeah. Well, at the end, basically you can design this signal interference filter to ideally provide you comparable performance to more classic filters. So at the end, the dispersion that you obtain at the end is also the one that you get from the technology that you are using. That, for example, if you are using transmission lines, you will not have a lot of dispersion when compared to if you use waveguides, for example, because in waveguides, you know that the phase constant is not linear with frequency. So waveguides are more dispersive transmission media than transmission lines. So at the end, and in more conventional approaches, I would say that the level of dispersion that you achieve is mostly the one that you get from the own technology. So you don't find significant drawbacks from using this approach when compared to some other solutions, because at the end, it's the own technology, the one that mainly defines the dispersion level that you get.
Okay, thank you. Regarding the filtering amplifiers, can you please refer to the linearity and noise performance limitations of this approach?
Yeah, this is a good question. So at the end, to be honest, here we have this filtering power amplifier. I can tell you that the noise performance that you get is mainly defined by the low noise amplifiers that you are putting in each branch. And then you have an advantage in terms of not linearity behavior, but this is the advantage that you mainly get from the two-branch architecture, because in order to acquire a given power level at the output, each amplifier needs to be or needs to support just half of the power. So at the end, let's say that in this device, the advantages that you get in terms of nonlinearity are the one that the amplifier, the two-branch amplifiers can provide you by itself. Adding this filtering capability maybe can help you in terms of the third point intermodulation product, because maybe can provide some filter depending on the space that you have for when you do the measurements between the tones. But I would say that adding the filtering capability doesn't suppose in this case an advantage in terms of nonlinearity or noise when compared to what you already get from the own two-branch amplification arrangement.
Thank you. And the last question, as far as I see it, how do you reconfigure in real time?
Yeah, this is a very, very good question, and this is a very, very big problem.
Sorry.
Because at the end, all these devices that I have presented here are just proof of concept prototypes in which we validate reconfiguration by mechanically tuning capacitors. But you are right that in order to make all these highly reconfigurable devices useful in a real application, we need to obtain or to design real-time reconfiguration or automatic tuning tools for all these devices. And this is something that, from my viewpoint, is making that these kind of devices didn't find yet a direct application on real systems. So basically, the question that you propose is a big problem. And now there are some groups that are working on the automatic tuning of this kind of filtering devices, so that, for example, if you have an interference at the input, the own system can position one of the stop bands that it creates to suppress the interference by recognizing by itself the presence of the interference. But for that, you need very complex automatic tuning tools, signal processing blocks and algorithms that allows you to do this automatic tuning and so on. So in reply to your question, this is a very good question that up to now didn't find a very good solution. So now some groups are researching into that.
Roberto, thank you very much. I think there are no more questions. This is the last call for the questions.
Okay. So thank you very much. So if there are no more questions, I would like to thank you again for your very kind invitation. And I hope to have the opportunity to visit you, Technion, face to face at some point, because for me it was a great pleasure to be here today. Technion is a world first-class level university and research center. So I really hope when this pandemic passes to have the opportunity to provide a more complete course in the future there. So thank you very much.
Thank you, Roberto. We will be waiting for you to visit in person. Thank you very much.
Thank you very much.
Goodbye.
Goodbye. Bye-bye.